Hey there, Chem Scholars. Today we're going to talk a little bit about light and waves and how that affects this whole idea of electrons that we are talking about with our electron configurations. You might be wondering, what does light have to do with this? But it actually has a lot to do with it. What we understand about electrons comes from what we can see, and we see light, right? So when we give energy to different elements, specific colors will be given off of that in return. So for example, if you've seen a neon sign, okay, we put electricity into that neon gas and we get a very specific color pattern coming out of it that we know is specific to neon. And that's specific to neon because of the electron configuration of neon. So we're going to kind of work our way towards understanding that a little bit by talking about light. Now, when I say light, please understand that I am talking about the entire electromagnetic spectrum. We could be talking about radio waves, microwaves, X-rays, gamma rays, and this whole spectrum. We talk about light because it's a part we can see. But you notice it's a very tiny part in the middle of the spectrum. Okay? Compared to everything else, it takes up very little space. Okay? You'll notice that the visible spectrum goes from roughly 700 nanometers to 400 nanometers. I'm going to explain why nanometers and what that means in a moment, but keep that in mind. All right, so you see a couple terms here, wavelength and frequency. Those are typical terms for waves. So let me shift my view here and talk about waves for a moment. Okay? A typical wave-like pattern represented like this, that's sometimes called the sinusoidal wave. Physicists will call it a transverse wave. It's a wave pattern. Okay, waves have a couple different properties, but we're going to focus just on two of those that you saw on the chart there a moment ago: wavelength and frequency. Wavelength literally is the length of a wave. Its formal definition is the distance between corresponding points of consecutive waves measured in meters. Okay. Now I said measured in meters, but small distances might be in nanometers, and that's where we were seeing those colors that I'll backtrack to in a moment, from 400 nanometers to 700 nanometers for visible light. Frequency is defined as the number of waves passing a given point per second. So if this time frame on the board represents 2 seconds, I would say the frequency is 2, and the units are called hertz, although hertz really just means per second. You'll notice that there are some weird letters written by the symbols. Wavelength is measured, the symbol for wavelength is a Greek letter lambda, and frequency, the symbol is nu. That is a Greek letter also, even though it looks like a V. So a lot of students like to use W and F for wavelength and frequency. That is your prerogative, but I'm going to use lambda and nu, okay, wavelength and frequency. So if we go back a second to the other view, you see the wavelength with the lambda, you see the frequency with the nu, and you'll see that the wavelength increases on this graph from right to left, but the frequency increases from left to right. So they are clearly inversely related. As one increases, the other decreases. Let's talk about the logic of that. Bigger waves, if it has a bigger wavelength, then it's probably you're not going to see as many pass a point at a given time, and so it must have a lower frequency. Okay? Likewise, if it has a high frequency, that must mean that there's a lot of them going by, which means they must have a very tiny wavelength. Now, just to emphasize that idea, at this point, radio waves have a wavelength of 10 meters. Okay, so that's, a little over 32 feet, almost 33 feet. Okay, and at that point, the frequency is somewhere around 3 times 10 to the 7th. Around 3 times 10 to the 7th hertz. At this end, okay, down in the cosmic rays, which is really just part of gamma rays, but some people like to specify them a little bit more. We see that the wavelength is down in around 10 to negative 14th, okay? So that is very, very, very tiny wavelength. but the frequency is 3 times 10 to the 22nd. That's very large. Okay. So we do see that inverse relationship there. And as I mentioned, the color spectrum you see by wavelength, it says lambda 700 nanometers, 400 nanometers. So when we talk about the wavelength, relates directly to specific colors. All right, so with that in mind, there had been a little debate a little over 100 years ago, 150 years ago, not quite. Anyway, scientists were debating, was light made of waves or was it particles? Now we've just been talking about waves, so you're thinking, well, clearly it's waves, except waves cannot travel without a medium. Okay? You can't have sound without air. That's why sound does not travel in space. Okay? There has to be a physical substance that is conducting the wave, just like the ocean would not have waves if the water wasn't there. Well, it wouldn't be an ocean either. So people debated back and forth until finally they decided, well, it had to be both. And a man by the name of Thomas Young theorized that light could be comprised of particles that move in wave-like patterns. And an important scientist that we talk about, Max Planck, most people just say Planck, proved that light does have tiny particles that he called photons, and he was actually able to show some relationships that we're going to look into today about those photons. So we're going to talk about how those photons are created and how we notice them and whatnot. So we're going to go back to talk about light a little bit. Light travels through space and pretty much in air at a speed of about 186,000 miles per second. Okay? That is intense speed. In the metric system, it works out to be 300 million meters per second, or 3 times 10 to the 8th. The symbol for the speed of light is c. So c is always going to be 3 times 10 to the 8th, or 300 million meters per second for us. We use metric system. I gave you that number just as a reference, but this number is very important. Please make sure you have that down. C equals 300 million meters per second. Now, we talked about, wavelength and frequency alternating with one another, being inversely related, and that's because they relate to speed, and the speed is a constant, so as one goes up, the other has to go down, kind of relating to Einstein's theory of relativity. The speed of light is equal to the wavelength times the frequency. So again, for those of you that like to use the W and F, there it is, but I am always going to use lambda nu, wavelength times frequency. However, Planck went further to talk about the energy of these photons, and this is considered Planck's law. Energy, E, equals H, Planck's constant, times frequency. Again, the more formal way, instead of F, we use the Greek letter nu, E equals H nu. H is called Planck's constant. It is a constant. It's the same thing every time, so this is another number you need to write down and keep track of. Maybe stored in your calculator, like I told you how to store the other number for the mole, 6.02 times 10 to 23rd. You might want to store this number just to make it easier for yourself. Okay? These two equations are essentially the big part of tying the whole idea of light, of the light being given off by something back to the electron. So relating that neon light's color back to the idea of its electron configuration. So we're going to talk about that next. But first, make sure you understand about the units of these things. Speed is going to be measured in meters per second. So we're always going to use 300 million meters per second. So the wavelength has to be in meters if we're going to talk about meters per second. Frequency is measured in hertz, which is essentially just the same thing as 1 over seconds. So you have meters, you have 1 over seconds, put them together, you get meters per second. Energy is measured in metric units called joules. We'll get into the joules a little bit later. It's based on the idea of kilograms, meters, and seconds. For right now, I just want you to know that it is measured in joules. All right, so let's put this to work. If the wavelength of a photon is 425 nanometers, what is its frequency? And how much energy would the photon in the previous question have? All right, if you want to give it a try on your own, pause the video, give it a try. I'm going to go on and explain it now. So here we go. Speed equals wavelength times frequency. We know the speed is always going to be 3 times 10 to the 8th meters per second. And we know the wavelength was 425 nanometers, where nano means 10 to the negative 9th meters. So 425 nanometers would be 4.25 times 10 to the negative 7th meters. Then I rewrite the equation. Frequency equals speed divided by wavelength. So now I take the speed, 3 times 10 to the 8th meters per second. I take the wavelength, 4.25 times 10 to the negative 7 meters. Divide them out. I get 7.06 times 10 to the 14th hertz. Now that's the answer to the first part. The second question was about the energy. So now we go on to our second equation, E equals h nu, where h is Planck's constant. So this is always going to be the same number. But the frequency was just found in the previous part, 7.06 times 10 to the 14th hertz. So now I just have to multiply those two to find out that my energy would be 4.68 times 10 to the negative 19th joules. Okay. It is a small number. That doesn't matter. We're only talking about one little tiny photon. Okay. We're going to be hit by moles of photons, so we're going to get lots of energy over time. So don't worry about that, the fact that it seems so small. So what does that number represent? Again, it's just how much energy that particular photon is transferring, because waves transfer energy. All right, you're going to do some more practice on that, but let me just kind of tie this idea together a little bit, try and explain it a little bit more. So give me 2 more minutes. We mentioned the idea of neon signs. You may have seen elements being heated in flames. I shouldn't say elements, substances being heated in flames, and you get very specific colors, right? That's where fireworks are getting their specific color from. It's relating to different substances. And we've seen different types of neon signs. They're not all neon. Different elements will have different colors. And that kind of relates to this idea that there are different, when elements are viewed through a spectroscope, we see that what color, for example, neon was giving us is really a bunch of colors blended together. And each of these little lines represents a specific wavelength in nanometers, which then means it relates to a certain amount of energy because of the way the electrons are being jumped around because of that added energy to it. So the energy is causing the jumping, which in turn creates these lines. So that's really the basic idea. Every element has its own unique set of spectral lines, and so that means that every element must have a unique pattern of electrons, which is those electron configurations we're talking about. Now, again, we're only looking at the visible part. Really, these lines would go in the other end, so they go out into infrared and they go out into ultraviolet. We can't see that. We're going to just focus on this. But there are devices that can see those lines, and we'll go into it more. So the idea here does tie into what we've talked about already, that every element will have its own unique pattern. And if we view it through a spectroscope, which is a lab we may or may not get to because COVID, but we'll see. It does tie into the Bohr model because Bohr was the one that, when in his model, talked about the fact that when atoms absorb energy, the electrons have to jump to different energy levels, and when they go back in, they have to emit energy. And how much they jump, obviously, the bigger the jump, more energy is needed, and more energy would tie into a bigger frequency, which would tie into a smaller wavelength. So all of these things tie together in a nice little package. So there you go. You're going to try a couple of these questions on wavelength, frequency, and energy. And that's it for today. Ciao for now.